Hey, it's Matt from Matt on Data Science. I want to talk to you about a portion of a conference talk I gave just actually last week, where I spent some time going over an open source project called OpenRA. OpenRA is a C# project built to emulate Command & Conquer, Red Alert, Tiberian Sun, Tiberian Dawn, and Dune 2000. This project started in 2007, and it's had a lot of public contributions to it. And I'm using this project as an excuse to take a look at what we can do with our source control and how we can get data from our projects, whether they're open source projects or business projects, and just take those projects and get some data out of them and visualize that data in a way that we can find some trends or communicate some insights to business stakeholders. So let's take a look at the process of getting the data out and visualizing it. So there's really four basic types of data that we can work with in a project. There's going to be information about releases, like when we actually release our software, information about work items or issues. For this OpenRA project, that was GitHub issues and GitHub releases were what they used to track those two types of items. And then there's the more obvious types of data associated with the project, such as the actual commit data. So with source control, anytime that you are making a change to a file, you are making a commit. A commit may modify one or more files, so you may modify 2 files at once or 4 or whatever it might be. And throughout the course of a day, developers are making multiple commits on your projects. So you have a lot of commits flowing through your project, which sort of illustrates the history of your project and what's being worked on when. Additionally, you have some raw data from just the file structure, so the directory structure of your application, or your code base rather, and then the types of files in there and the size of each file. So you can kind of look at all 4 of these different things and start to get some insights out of your code. So I've got a Jupyter notebook here. That's Jupyter with a PY. I have another video and article series on that if you are curious about what that is. But here we are grabbing out the Pandas library, and then we're grabbing out some data. So release data is pretty easy to get from GitHub. We actually install the GitHub CLI or command line interface, and then from the terminal we just run GH for GitHub, release, so we want release information, a list, and this is going to give us a list of all the releases. But then we're going to pipe this into a releases.csv file. And that releases.csv file, that just looks like this. So it's a very simple file. It doesn't have any headers whatsoever, so we have to add those on our own. But it has information about all the various releases that we have. And I am piping this in as a tab delimited file, even though it's a CSV for comma separated value file. That's just because some of the files that we worked with actually did have commas in the various fields, and that threw things off. I tried to use pipe delimited, but they had some pipes in some of those commits too. So I wound up using tabs as my common delimiter. But we are loading our release data. If you're curious about my cleaning process there, I have some extra factors I do for this, where I'm basically taking a look at all the data aspects of it. I'm finding any releases that might be tagged latest and just renaming them to release, making sure that dates are representative of dates. But I have this little data frame here as a Pandas data frame that represents 2-dimensional data. And this is just the top 5 rows of it. Next, I'm creating a collection of release lines. This is a set of lines that I can include in a Plotly Express or Plotly chart later on. So I'm using Plotly for some data visualizations. So I'm just building out an array of these line dictionaries. And each dictionary item looks a little bit like this, which is a little odd to look at, but it's what Plotly needs in order to chart it properly. And we'll see that coming into play a little bit later. Issue data, because this project is working off of GitHub issues, I'm using the GitHub CLI again. I'm saying GitHub issue list, but then I have to specify the type of issues that I want it to pull back and the maximum count. In this case, I wanted all the issues, and so I picked up all 10,000 of those issues, and I'm working with those. Well, actually up to 10,000. I think it was only something like 6,000 issues, something like that. But I want issues that are either open or closed. I don't care about the state. And again, I'm piping it to issues.csv. And that looks very similar to the releases one, except it's much larger in scale. One thing to note here This red alert, question, support, artwork, this is all one column in our data set. So we need to do some more intelligent things in how we split it out. So based on what's in the labels column, we're actually coming in and we're adding in some additional columns just to be able to work with things here. So, so there's some cool stuff going on in this just to pull out all that data. Get commit data. Commit data is harder to pull out. The GitHub CLI does not currently support getting out commit information at the time of this recording. It may at some point in time, but right now you can't get individual commit information. So there's two different ways of getting commit information from Git. The first way would be to do what I did and use the library called PyDriller. PyDriller can work with an open source, a public GitHub repository, which is what I used in this project, or it can be pointed at a local folder that happens to be a Git folder. So if you have any sort of a Git folder on your machine, you can give PyDriller a URL as far as the local repository goes, and it's going to go in there and it's going to interpret that. Now, using the public GitHub API was very slow for this project. I think it took me about 8 hours for a total run for this. This is a large project, but still, 8 hours to pull down that data is a long time. And so this is overnight runs for me. It'd likely be a lot faster pointing it at my local machine, but I'm not certain how much faster because PyDriller does do some additional analysis as well. But we get information out about the commits, such as the hashes, any sort of messages associated with them, who made the commits, what files were impacted by it, the number of lines added and inserted and deleted, the net lines of code, the number of files affected, things like that. And I'm kind of engineering some like day of the week columns and year columns and things like that just to make my job a little easier. One note here, with GitHub, with any sort of commit information, you're going to have some kind of noisy data where you're going to have people with multiple names committing to your project over time. For example, if I'm working from one computer, I might be authenticated as Matt E, and if I'm working for another computer, I might be showing up as Matt Eland. And so I need to be able to merge both of those two things into one user. So anytime you see one or the other, treat it as me. So that's kind of what we're doing here. Is we've looked at all the individual contributors, and we find cases of where they were duplicated, and we're just sort of renaming them to the common one they should have. And we wind up with something like this, which is just a little cleaner, and we see Chris F is now Chris Forbes. This is a nice example. File system stuff, there's not really a good library for that. You sort of just write your own, but that's a pretty simple process. You go over and you loop over your directory, you find all the files there that match a certain filter. In my case, I cared about the .cs files for C#. You'll open them, you'll read each line, and you count the total number of lines. You don't care about the contents of the lines. You just care about the quantity of the lines. And you wind up with something that looks a little bit like this. You have this whole directory structure of your project with information about the various files. So now that we have our 4 different types of data sources, we can start to do some analysis on them. The first thing you might do is statistical analysis. You can look at this distribution of things. So for example, if we're taking our data frame for file information, the one that we just built, I could do a describe on it. Describe just basically gives me statistical information about the columns of that. So, for example, the lines, this is the lines of code in that file. I can see that there are 1,300 files, so 1,362 files to be exact. The average size of a file is 136 lines of code. The minimum lines of code in a file is 18, and the maximum lines of code is 1,411. I actually feel really good about that 1,411 number. It's a big number, but for that to be the largest file size in the project is pretty good from my experience in .NET projects and C# projects. The average file size of 136, that's also pretty good. One of my barometers for whether or not a file should be, a class should be improved or split out into multiple ones is if it's over 200 lines of code, it probably needs to be split into multiple files. So already I have some information about really the quantity of files here and the size distributions. But that's not very visual. And so we can get into some visualizations here. There's a lot of different ways you can visualize things in Python. I really like to use Plotly. It's a data visualization library. I like it because it's very interactive, it's very attractive visually. You get a lot of nice features just right out of the box with a single line of code. And they offer 2 APIs, so you can use the Plotly Express or PX API just for very simple charts, which is most of what you're going to be doing. Or you can use the Graph Objects API to build more and more custom things. So you'll see a little bit of a mix of both. I definitely prefer the Plotly Express, but I work with both. So I'm setting up some common variables, some ways of renaming things. So when you see average net, show it in the chart as an average net lines, for example. Defining some common functions just to show things in a standard way. So if I ever wanted to tweak my themes, I could tweak them in one place. If I ever wanted to tweak the height of something, I could tweak it in one place. You don't have to do that. I just found it was helpful for me for this project. So now we get into our visualizations. So we'll start with files. Now looking at this project, this is a histogram of the frequencies of various file sizes throughout the project. So if we look over here at this large peak over here, we can see between 60 and 79 lines of code. There's roughly 200 and we'll say 20 total files. Most of those files are in this green band here. I'm kind of colorizing here by the project. So here I'm saying Plotly Express histogram. I'm giving it the data frame of files. The x-axis should be the lines of code. I'm giving it a title, and I'm giving it some information about how to display things with the labels thing. I'm also giving it a color scheme, which works well for me here. But this lets me see which aspect of this project takes up the most space. So, and if I wanted to just exclude one, so this green is really a lot. So if I wanted to hide it from my results, I can just click it. Additionally, I can zoom in to this particular region. So for example, things over 200 lines of code, I said I don't like that very much, so I can just draw on the chart and just zoom in on that area. And if I wanted to zoom in even further, I can do that. So Plotly Express gives me a lot of stuff just out of the box with a single line of code, which is part of why I like it so much. But this shows me that we have this OpenRA mods common, this green one. That's most of our code in this project. So it tells me the code is not evenly distributed, but most things tend to be in a pretty good distribution as far as the number of lines of code in a file. So this is a good chart. Looking at the same data here in a box plot, this is more of a statistical representation of our data. It's showing me really the median points of the data for each project. And I can see again, OpenRA mods common, the median value here, and this gets a little hard to read when you mouse over it, but the median value is 84. So the middle value for everything is 84 lines of code per file in this project, which is great. But then you see all these little green dots, and these are our outliers. And we can look at each one and we can see which file it is. So this is the lobbycommands.cs or C# file. It has 11,000 lines of code. I can look over here and see my largest file in the project is server.cs with 1,411 lines of code. So looking around over here, I can see a lot of different things. I can see my test library has only a few things, and I can see really the areas I might need to focus on if I was going to be doing some refactoring. I might care mostly about the game and the common libraries. I can visualize a hierarchy pretty easily using the tree map. So here I'm creating a tree map. I'm grouping by well, really everything, and then the project, the path within the project, and then the file name within that path. So here we can see we've got our common, our game, our command and conquer mod, things like that. I'm also colorizing by the project, so you can kind of see everything is sort of distributed into various neighborhoods. Some of these things are very small, so if I'm curious about it, like server traits, for example, I can just click it, and it zooms in, and I can see what composes the server traits path. I can see it's mostly this lobby commands. The size of things is determined by the lines of code that they have. So this one actually has 1,100 lines of code. And I can look over here, and this lobby settings notification has 42 lines of code. Very good number. If I wanted to zoom out, I can click on a higher level of zoom to zoom out to the project, or all code to zoom out to the entire thing. So again, I'm doing all this with a single line of code once I have my data arranged into a data frame. So that's really neat. Let's take a look at a different coloration. So here's the same data, the same hierarchy, but now we're colorizing by the line of code. And now we can see the larger things are not only are they bigger like they were before, but they stand out because they're bright yellow versus dark purple. So what we colorize on tends to matter quite a bit for helping us interpret a tree map. I typically like to have my size or my values here be the lines of code unless I have a compelling reason to use something else. But typically lines of code is a good one to go off of for a tree map. Sunburst, I like to call these things the pie charts from hell. This is basically a nested pie chart. So we're looking at the same hierarchical data as we were over here, but we're nesting it in a pie chart. So for example, OpenRA game has all these things inside of it. And I can click it and it'll just zoom me in on those areas. And I can click again to zoom in only on the map areas and see, hey, what's composing my map directory. Same exact thing as the tree map, but this lets me see my proportions a little easier. I don't find this one is very helpful frequently for sharing with other people because it's so weird, but it is pretty, and it helps you see a nice view of proportions. We'll take another look at this later on when we're looking at contributors. Commits. So here I'm looking at commit data, so commit history over the years. So per year, what level of traffic are we getting? And you can see I've got a lot of coloration going on here. If I wanted to get rid of that coloration here, all right, now I'm colorizing by the weekday, but I can just comment that out and run that chart again, and now it's all just purple. But as I'm doing data analysis on my own, I tend to look at as many different aspects of my data as I can, and then when I'm sharing my data visualizations with other people, I'll simplify it down to make it less and less busy so they can focus on really the core things. But here we're looking at the amount of commits per year, and this color is the amount of commits on a given weekday. And looking at 2010, it's fairly evenly distributed between all the different days of the week. You do have this bias towards, looks like Friday is a pretty heavy day. Saturday and Sunday get a decent chunk versus looks like Tuesday is not a very active day. But mostly they're pretty equal to each other, these days are. Now you go over here to 2015 or so, and you can see it's very clearly you're having a lot of commits on Sunday, a lot of commits on Saturday, and it's not as evenly distributed. This is because 2013 to 2015, this is when this project really pulled a lot of different authors in. And so I think you have kind of this baseline level of commits from your community, but in your peak times, your peak years when you had a lot of people contributing on it, a lot of those people during that time were maybe weekend warriors, might be a word for it. They were just committing mostly on the weekend. And so you can see the changing nature of the graph due to that. But it's still, everything's bundled by the year. So let's take a look at it bundled by the month of the year. And now you can see the same data, but now we're breaking it down a little bit more, and you can see a little bit more about what areas are getting contributions. So this helps me find that, hey, in December, we are not getting a whole lot of commits historically. So Decembers tend to stand out a little bit more because they tend to be the lowest month of the year for the project. And here we're colorizing again by the day of the week. That's not as helpful in this view as it was at the year level. You also see that we have these little dotted purple lines over here. These lines represent the individual software releases for OpenRA. So we can see just before 2018 it was released, and then it kind of was released almost at random, it feels like, after that point. Additionally, after the point where it was released, you stopped having the massive amount of commits coming in. And that's really more evident over here on the yearly level than it is on the monthly level. But you can see the activity just really plateaus once you hit your release years, which is what you'd expect from a project that's finished and is now entering maintenance mode. Here's the same data, but now aggregated down to the week, and you can see compared to the month, it's a little harder to make inferences off of things. It's a lot more noisy. So aggregating things at a certain level is helpful for you, but you need to figure out what that level is, whether it's the week, the month, the quarter, the year, whatever it might be. Here is a scatter plot. Scatter plots are one of my favorites. They're not as attractive as many of these other things that we're looking at are, but they're very helpful for determining correlations. And so as I'm analyzing data, I'll take a look at all sorts of different things, and I'll put it on the X or Y axis and just see what trends I can find. And here we're looking at the number of lines of code added per commit on the X axis, and the number of lines of code deleted per commit on the Y axis. And you can see there's some very strong trends here. So on the Y axis, you have this trend of having a lot of commits that delete a lot of code but don't add a lot. On the X axis, you have the same trend where we're adding a lot of code but we're not deleting a lot of code. But we also have this diagonal correlation line, and that goes all the way up here to a data point way up over here. We'll talk about that in a second. But this is where we're adding and deleting roughly the same number of lines of code. So these are probably more refactoring or just universal changes. I mentioned this point in the upper right. Scatter plots also help you find outliers pretty easily. So this one outlier over here, this is where a fellow named Paul Schote has added 43,000 lines of code and deleted 43,000 lines of code and modified 489 files. And it looks like he's updating copyright headers. So this commit kind of stands out. So that helps you find outliers and identify things you might need to investigate a little bit more on. Here I'm colorizing by the net lines of code. The colorization doesn't do me a whole lot of good on this chart. It is kind of pretty, but the data is so fine-grained and so scaled out that it's hard to make anything of the colors. But I always like to work with my extra dimensions if I can. So here's another scatter plot where the Y dimension is the net lines of code, so lines added or lines removed in that commit. So we're visualizing individual commits to this project. The X-axis, instead of being a time axis, we are now looking at the number of files modified. So most of our changes aren't modifying a lot of files, and they're getting close to this zero axis. But what you're going to note here is that I have this color axis, and the yellow values here represent things closer to the current year, and the purple values are things closer to the beginning of the project. And what you can see is that as you get closer and closer to the current year, as we get more and more closer toward our yellow colors, we have more this tendency to be grouped closer to this 0, 0. We're modifying fewer files, we are modifying fewer lines of code. And that's a sign of the application is really starting to cool down and get a little bit more stable. The changes are becoming less drastic, which is what you'd want to see from a project that has matured and hit release level. Kind of a different chart, but I think it does tell a story, and that's interesting to share. So here I'm doing some more grouping to support things at a different aggregation level. But then I'm doing this little artistic chart here, where I'm graphing the individual commits on the X-axis. So each one of these is a day, and the Y-axis is the number of commits for those days. So we can see the level of activity that we have in our project over time. The coloration is the number of authors who contributed on that given day. And so you can see that things are closer and closer to purple on these more extremes. But in our heyday of this project in 2015, 2016, you have some very bright colors where you have maybe up to about 12 people per day making commits on this project. You can also see spikes where you have a whole lot of commits per day. And you have these little troughs where you don't have as many. You even have periods of time when you have no commits whatsoever, where the project looks like it might have died. And here at 2012, it looked like it was about to die again, possibly. But then it really sort of spiked itself off. So nice, colorful way of visualizing a project's history, but not a standard graph, so it's going to be a little harder to communicate to other people. But still valuable as something to discover insights about data as you are personally exploring it. Also would make a nice wall print. Here's more of a standard chart where we are looking at the net lines of code changed per month, rolling everything up to the project level. You can see it looks almost like a seismograph or an EKG or something like that, where you have this massive period of instability from 2012 to about 2016, during the heyday of the project. And you have some massive additions and massive deletions to your project. Now note that 2010 we have this what looks like a minor disturbance here relative to the other periods of time. And note over here at the right edge that once we've hit our release mode, the project is not getting a whole lot of activity as far as the scale of the commits, which is good. You don't want massive commits after you've been out there in production. People are relying on you. But let's take a look at this data a little bit differently and keep this region over here in mind. So here we're looking at the same exact data, but now we're charting both the lines added and the lines removed on the same graph. And we can see during that period where it didn't look like there was as much activity, the spikes of the lines added and lines deleted are roughly equal to most of the spikes during the project's heyday. But because they were in the same month, they really canceled each other out on that prior graph, and so it didn't look like it was as severe of changes. But it really was fairly drastic structural changes that we were seeing during that time. These purple dots in the middle are just the net lines of code, so it's just the addition of these two data points together. And this does highlight, this period of maintenance mode as well. So this is weird, but Plotly does give us the ability to do a 3D scatter plot. So instead of saying scatter, we're saying scatter 3D, and we just give it a z dimension. Here the z dimension is the number of files that we have. And so the files modified is now showing up on my z-axis. And here I can look at this and I can see three-dimensional correlations. And this chart that I'm looking at right here, this looks a lot like the chart that we saw a little bit ago with all that activity. It's that same exact line of data where we're looking at the number of files in this case, the net lines of code on this x-axis, and this, what we'll call, I guess, the y-axis here is just the date. One of the things that's really interesting to me about this particular graph is this vertical curve. And what we see with this curve is actually, I believe we're looking at the total number of lines, total number of files in the project. So you can see the files modified. It sort of increases on these little outlier commits over time. I think these are just commits that modify all files in the project. So you can see really the scale of the project growing over time. So not necessarily a helpful one for showing to an executive, but it's pretty cool that I can add a third dimension just by adding underscore 3D and adding a Z column, and it helps me find more correlations. Color is its own dimension as well, so you can now almost have a four-dimensional data here. And you can do animation as well, maybe over time or whatever. I don't have any animation examples for you here today. So contributions. So this project had a lot of contributors, and I actually had to do something fairly absurd. I had to filter out contributions from anybody who made fewer than 100 commits in order to make this particular graph readable. I've never had a project before where I had to filter down to people who have made 100 commits or more, but that's what we had to do here, because this project has just had so much open source activity. But here we are charting basically a bubble chart of the various contributors on the Y and color axes. You can see their activity over time. So here we see Chris Forbes kind of kicked off this project in 2007, and then it hit kind of a lull, and then 2010 it really kicked off in earnest with Chris and Bob and Paul really kind of kicking things off. Chris is a really interesting one because he has these massive spikes, and in fact here in January of 2010 he has 360 commits in a single month. And then after that, it sort of peters down a little bit. You have some resurgences a little bit, but largely Chris starts fading from the project, relatively speaking, and other people start taking the helm of the project to the point where Chris is largely uninvolved after a certain point, and you have other people really taking the reins and running with the project and building it to completion. I think this is a beautiful chart because it shows the life of an open source project. It shows people coming into the project and leaving the project. It shows seasons of life for various contributors. You have people who are contributing a lot in 1 month and then not a whole lot for a few months on end, and they come back strong. And I think that's really a big story in open source. I wish I could show everybody on this chart and have it be readable, but due to the scale of data, I really can't. But I think this is really fascinating to look at data like this, and I want to try this with more projects. Here's the same data, but instead of looking at the y-axis being the contributor, we are now looking at the y-axis as the net lines of code changed. There's so many different contributors here, it's hard to tell what color represents which person, but you can sort of start to see some patterns around certain people, like whoever this blue person is over here, Matthias, it looks like, tends to have this pattern of having large deletions, versus whoever is red over here, Reaper, tends to have smaller scale additions than some other contributors. So each person has almost their unique thumbprints. You can see from their patterns of commits. Another 3D chart here. 3D charts are not always helpful, but they're usually entertaining. Okay, so here we've got our year month representing things linearly. Our commits are representing the number of commits in that month. The authors is our z-axis and our color axis. So we can see as time went on from the start of the project, the number of contributors grew quite a bit. It's making intelligent guesses about where it should render things, not always guessing it correctly, until we really hit this heyday in this 2015-2016 period, where you had a lot of contributors, a lot of commits active on the project. And then you got past that, and you started getting closer and closer to release. And as you did, people left the project more and more. The scale of commits drastically went down, and to the point where the project is largely just in support mode. This is not a dead project. This is a successful project. So just keep that in mind. They achieved their goal. You can go to openra.net and download Open Red Alert and play it for free. You can also take a look at their code, all 133,000 lines of it. Okay, so let's take a look at their issues. Just see what issues they have in this project. You can see most of their issues are closed. They're in the closed status. That's our color and the size of these bubbles, as well as the y-axis. They have a number of open issues, and that number of open issues seems to be growing over time relative to what it used to be. But still, a large majority of their issues are closed. Though as time has gone on, more and more issues or fewer and fewer issues are closed. I believe this is probably a function of the number of people on this project, if I had to take a guess, without really being deeply familiar with what's going on. I say as you get fewer and fewer people on the project, you have fewer and fewer people to investigate things. You may also have just bugs that are very hard to investigate or resolve, and so they tend to stay open but not really actionable. So if you wanted to help this project, they might need some help with just triaging issues. I don't know that for sure, but it's just a guess I have looking at this data. Issues by type. I can see they have a number of support kinds of things. It's not very high, but they do have some support things. Interestingly, the quantity of support requests that they seem to have gotten decreased after the initial release. So this is probably people trying to figure out how to build a project, and they're like, no, look, here's a build, go run it with it. Again, this is just me making guesses about things, reading their data. Overhead, this is refactoring things and little chores, things that are not necessarily moving the project forward, but you need to do to have a healthy code base and a good team together. Then you have features and bugs, and you can see bugs are predominantly the type of thing that we see in the issue system, followed by features. Don't see any huge trends as far as years go. We can represent about that same data in a heat map. So this is the same thing, but in a more standard format. So now we're not representing it with a bubble and a color, we're just representing it by the color. And that helps little outliers like this August 2020 massive spike of bugs, or this, looks like, come on mouse, December of 2014 massive feature request spike. It helps you see those things a little bit more clearly. You can look. We're grouping things now by game, and you can see there's not really a hotspot for game-wise. There's maybe a few hotspots around Red Alert, but other than that, most of the things are not associated with a particular game. So it would help us determine if we had a game that was maybe a lemon or having issues in certain periods of time. Here we're charting the number of bugs, bug tickets created per month, bug issues created per month. And you can see there's a lot of noise to this. One of the things I look for with a chart like this, I like to see if there's a massive spike in bugs after a release, indicating that potentially we broke some things with that release. And we don't really see that. Instead, we see maybe a slight increase a few months after a release, in this case a pretty massive increase. But I'm not so sure that these are caused by the release. This might just be caused by regular usage patterns. So I'd be curious to get a hold of some download data or something like that for this project, and just see when the project is seeing more usage versus less, and compare that to our issue data. So here we're charting the status of issues over time. So as you can see, as we're going on, in the beginning, almost everything was from a certain year before is going to be in the closed status, so it's got a very high probability of being closed. But as time goes on, we can see issues are trending more and more to be more likely to be open than likely to be closed. It's not a strong trend, but it is a it is a gradual sort of a descent towards most things are staying open. We can take a look at support requests over time. This doesn't seem terribly helpful. This is again the percent closed. I'm not so sure how helpful this chart was, but it's always good to experiment and see what trends you can find, what aspects of the data you can find. So we can marry together our various different types of data sources, and we can do some analysis with it. So for example, if I wanted to see the number of times a commit occurred and involved a specific file, that might be something I might want to chart. If I wanted to see, hey, what percentage of commits on a given file look to be bug related, I could take a look at that. Now this project has a weakness in that they did not have a strong template for commits. So whenever they made a commit, the developer would write down whatever they wanted to write down, and each person did something different. Unfortunately, this means that we can't really trace an individual commit to a specific work item, to a specific issue. So I don't know for sure that this commit over here was a bug fix commit, or if it was a feature commit. I have to sort of do some guessing based on the text of the commit. So if a commit's text has something like defect or crash or fatal or error or something like that, I'm flagging it as a bug commit. And if it doesn't, I'm flagging it as a normal commit. There's a certain degree of inaccuracy there, but it's the best I can do with the data that we have. So my key takeaway for you is have your team get together and identify a standard way of committing, of making your commit messages going forward, just so you have the option of doing some mining on things at some point in time in the future. It's my biggest suggestion to you all. But once we have our data merged together, we can start to look at things here. So here we're looking at the date the individual files were first modified. We can see a lot of files seem to have been created in 2015, and then some, a pretty steady trickle of files were created after that point. I didn't expect as many files to be created after 2018, given kind of the release mode of things. But there were a decent chunk that were created on a regular basis. Another note here is that the earliest date a file was created seems to be 2010. This is because my current code here that I made for this project doesn't handle file renames very well. So I believe all code prior to 2010 has been renamed or deleted to something else, and so that's not really represented on this graph. So if you wanted to take my code, which I'm going to give you a link to at the end, or in the comments, actually. If you want to take my code and run with it, you need to be aware that it does have some limitations as far as renamings go. So here we're charting the last modified date of files. And this last modified date of files thing, we're now looking and we're seeing that most of our files were last modified of July in 2021. In July of 2021, there was a commit that modified all files in the project, or almost all files in the project. You can see the things to the right of this were modified after that point, but the things on that spike have not been touched since July of 2021. Now note that there are about 6 files, and it's kind of hard to see them given the scale of this graph, but there's about 6 files that have been modified prior, or that were last modified prior to July of 2021. And I'm not sure if they were simply missed in this project-wide rename, or if they were intentionally excluded. But that's an interesting data point, because if this should have modified everything in the file, I would expect this to be the leftmost thing in this graph. But it's not. Okay, switching gears a little bit, Let's take a look at the number of commits per file. So here we're colorizing things, with yellow meaning the most and purple meaning the least. And we can see that game.cs is bright yellow. It has had 633 commits involving this file. They might have involved other files as well, but they were at least involving this file. Mobile.cs has 204, server.cs has 370, 461 on traits interfaces.cs. It's interesting that there's so many modifications on a file that sounds almost inconsequential compared to game or server or mobile or map or something like that. So that makes me curious about that trait and what's in that and why that would change so much. In general, the single responsibility principle, or SRP, says that there should be one and only one reason for a file to change. And so for that one reason to occur so many times with game.cs seems unlikely. So it sounds to me, just from looking at this graph, that game.cs is changing more than it ought to. It could be that this project needs to modify this file anytime you're building a new build or something like that, in which case that's a legitimate excuse that file should change, but still, this is raising some alarm bells to do some further investigation. So here's a histogram showing the percentage of files that are, or percentage of commits on a given file that deal with bugs. So we can see a lot of files actually have no commits associated with them that appear to be dealing with bugs, but a number of files do have some minor percentage, around 12% we'll say on average, that deal with bugs. And we have one outlier over here, this file here, that has 50% of its commits that appear to be dealing with bugs. We'll take a look at that one in a second. There's some special notes I have on that file. We can see most of our commits are generally not related to bugs, which is a good sign. So here's the count of bug commits per file. Again, game.cs is very bright yellow with 131 bug commits to it. Server.cs is fairly bright as well. Mobile.cs, traits interfaces. In general, the files that have a lot of commits have a lot of commits that are bug commits. But that could just be because they had a lot of commits to begin with. So it could be helpful to take a look at the percentage of commits on a given file that appear to be bug related. And this is much more of a equal distribution. So we can see there's not as many things that stand out as bright yellow. There are a few things, but there's not a lot of them. So if I was to take a look at my bright yellow areas, I might drill into support, and I'd see perf tick logger has 50% of its commits that appear to be bug related commits. And so I might say, hey, that perf tick logger, that sure is buggy. But, not so fast, because that name, perf tick logger, that's more likely something that's going to help you find bugs than something that's causing bugs. They likely added this while diagnosing all sorts of crashes or slowdowns or things like that. So that's more of a solution than it is the problem, it would be my guess there. But we can take a look at this percentage thing and look for things that might be maybe a little outlier-ish. So 36% of commits to rectangle.cs are bug related. Okay, that might be a little alarming. That might not be a file that has a lot of commits, or that has a small number of commits associated with it. So if we find that was inside of hit shapes, so we can see, yeah, we got about 9 commits to rectangle.cs. So that's not a huge volume of commits. But we can take these two pieces of data and sort of marry them together and start to see, well, hey, do we have a significant number of commits over here and a significant portion of those commits look to be bugs? Okay, well, we probably need to start getting the quality of this file under control a little bit more. File ownership. So now we're looking at the most frequent author of a file, and this is probably the most helpful use of a sunburst chart that I have. So we can see Paul Schote is the most frequent author for any given file in the project. I suspect this might be that Paul is really amazing, and anybody really to show up on this graph is a pretty amazing person given the scale of this project. This might be that Paul contributes way more than other people, but I'd say it's also equally likely that Paul has a contribution history kind of like mine, where he likes to make really small commits versus a big commit that has everything fully baked out. So people who make a lot of frequent commits are going to show up a little bit more on things as the most frequent author. But this is a baseline to say, hey, like, hey, who works on this file the most? Let's say I wanted to see what happens if Reaper leads my project. I can click on Reaper, and I can see, hey, Reaper does a lot of maintenance around OpenRA mods common, and inside of that project, he does a lot of work with projectiles and traits. So if Reaper leaves, we're going to lose a lot of knowledge in these areas. It might be good to cross-train some other people in these things. And so that's where taking a look at the proportional things and being able to drill in per person is going to be helpful. Here's the same data, but in a tree map form, and we can see here we have our projectiles, and we can see, sure enough, Reaper owns most of that. I do like how the colors are shared between these two charts. It's a very helpful feature. You can see most of this is all Paul, but we do see some key areas like pathfinding, where we can see Rooster Dragon is a key contributor there. He's the main contributor. By the way, if you're ever looking for a hacker name generator, do a project like this and you'll find some pretty cool commit names, or contributor names. Finally, let's take a look at the relationship of files with each other. So if I wanted to see files involving game.cs, I could chart that. So this is the percentage of changes to a given file that also happen to change game.cs in the same commit. So game.cs is always modified in the same commit as itself. So it's going to be yellow for 100%. Versus, let's say, color.cs. Color.cs over here in primitives, 41.6% of the time when a commit occurs to color.cs, game.cs is also modified. For me, it's a little alarming how many bright colors I'm seeing on this graph. And this is actually why I made this graph, because game.cs has so many commits to it. The proportion of commits that also modify other files is very, very large on this. So this tells me that game.cs is being modified frequently alongside all sorts of other files. Note that you do have a trend where the smaller files, the files who are modified less frequently, tend to show up brighter. That's because they have fewer commits to them in general. And there are a number of commits that just modify all files in the project. And so that's why they appear a little bit more bright. But that doesn't explain things like this RGBA to hex.cs having an 83% correlation to game.cs being modified. Like, that doesn't make a whole lot of sense. So there's a lot of coupling, I would say, to the game.cs file. So here's another chart where we're showing the number of other files modified on average alongside a file. And we do see that trend where the smaller ones have a large number of other files. So ignores cloak.cs has 19 lines of code. In general, when it's modified, 931 other files are also modified. So that's a pretty absurd number. You can see that those are probably going to be commits modifying all files in the project. But this can help you find areas where you're having a lot of changes and maybe things aren't lining up that well with each other. So this has sort of been my experiment on this project. I'm going to follow this up with a couple of other videos exploring some other dedicated tools, commercial tools that will help me sift through the same data so you can see what it would be like to use a more polished tool for this. If you're curious about this code or my process, I'm going to write up a little bit more about my process on accessibleai.dev and probably go over it a little bit more in this YouTube channel. But I also created a site out there, mattelan.dev/visualizingcode, that gives you all sorts of information about this particular project. Getting the code, getting more information about how things work, being able to learn a little bit more about Plotly and Pandas and things like that. So give that a try. Let me know what you think. Let me know what you're curious about. I think it's really interesting to look at over projects, and if you do a similar experiment, please share a link to me. The best way of getting a hold of me is on Twitter at integerman, or you can email me at matt@mattondatascience.com. But thanks for watching. I hope you found this interesting, and I hope you apply some of these principles to your own projects. Happy coding!